Good morning, friends. Once again we are here with the next revision lecture on solutions of various kinds of differential equations. Yesterday I posted 2 lectures on solutions of differential equations in which I tried to cover variable separable differential equation form, reducible to variable separable, homogeneous, reducible to homogeneous, linear differential equation, Bernoulli's differential equation, exact differential equation, and 5 rules how to convert a non-exact differential equation into an exact differential equation 1. Now, today we will discuss the solution of differential equations of special type. In these differential equations, we will take dy by dx, we will denote it by p. We will denote it by p, and some special type of differential equations will be discussed. So, what are these special types of differential equations? These are the equations of the type function of x, y and p is equal to 0. Such type of equations we will discuss today. So, first of all, this equation may be solvable in p, may be solvable in x, may be solvable in y, or maybe some special kind of differential equation. So, we will discuss it one by one. First, I will take the differential equation of the type fxyp is equal to 0, which is solvable for p. So, equations solvable for p. So, I will take these equations first. We will solve these differential equations. We will illustrate the method using one example. So, here I am taking an example as p square minus p minus 6 is equal to 0. This equation is totally in p, containing no x, containing no y. That means the equation is solvable for p, and it is clear from the differential equation that it can be factorized. So we can factorize it as p minus 3 p plus 2 is equal to 0, which in turn will give p is equal to 3 or p is equal to minus 2. Now, what is our p? Our p is actually dy by dx is equal to 3, and here we will get dy by dx is equal to minus 2. This can also be written like dy minus 3 dx is equal to 0, or this can be written like 2 dx plus dy is equal to 0. And now the integration is very simple. Integrating both sides, the first one will give y minus 3x plus some constant of integration, say c1 equal to 0, or from the second factor you will get 2x plus y plus some constant of integration, say c2 is equal to 0. Either this is true or this is true. If this is true, then the product of these two, y minus 3x plus c1 and 2x plus y plus c2 will be 0. If this is 0, then the product will be 0. If this is 0, then also the product will be 0. So this equation will give you the final solution of the given differential equation if the equation is solvable for p. Even if the differential equation contains x or y, can be solved in this way. Now, the next one is when the equation is solvable for y. That means y can be expressed as a function of x and p. The equation is solvable in y, means y can be expressed as a function of x and p. Then how to solve this differential equation? Again, we will illustrate the method by taking some example. So I am taking one example as let y is equal to x plus p cube. Here y is expressed in terms of x and p. On the right hand side there is no y. That means y is expressed in terms of x and p. That means y, the equation is solvable for y. What to do? In such a case, differentiate both sides with respect to x. So here you will get dy by dx is equal to derivative of x is 1, derivative of p cube is 3p square, but that is the derivative with respect to p and we want the derivative with respect to x, so we will have dp by dx here. What is dy by dx? dy by dx is p. So this is p is equal to 1 plus 3p square dp by dx. Now we are having only two variables, p and x, there is no y. So we will try to solve it by using variable separable method or homogeneous form of differential equation or linear differential equation or exact form of differential equation, whichever is suitable. Taking this 1 to the left hand side, we get p minus 1 is 3p square dp by dx. Now it is very much visible that it is a variable separable equation. You can take p minus 1 to the denominator on the right hand side and dx to the numerator on the left hand side. You will get dx is equal to 3p square over p minus 1 dp. X is on the left hand side, p is on the right hand side, the variables are being separated, and now our main job is to integrate by using basic methods of integration. Integrating, what we are going to get? Integral of dx, we know it is x, but on the other side it is 3 constant outside the integration. In the denominator is p minus 1 dp. In the numerator we are having p square. Subtracting 1 and adding 1, we will get like this. That means 3 integral of p square minus 1 upon p minus 1 is p plus 1, because p minus 1 will be cancelled, plus 1 upon p minus 1 dp. And now the integration is very simple. You will get x is equal to 3, this is p square by 2 plus p plus log of p minus 1. This is the solution. Plus you can take the constant of integration as c. This is the value of x. Now substitute this value of x in this equation. So what you are going to get is y is equal to x plus p cube. This is your x plus p cube. So p cube plus 3 p square plus 2 plus p plus log of p minus 1 and constant of integration. Together these two equations will give you the complete solution of the given differential equation. X and y both are expressed in terms of p, and this is the solution of the given differential equation. So this is when the differential equation fxyp is equal to 0 is solvable for the variable y. Next, we take up the case when the differential equation is solvable for x. That means our equation fxyp is equal to 0 can be converted into the form x is equal to some function of y and p. That means x can be expressed as a function of y and p. That means the equation is solvable for the variable x. Again, we will take one example to illustrate the method how to solve such a differential equation. So let us take one example. Consider the differential equation P is equal to 10x minus P upon 1 plus P square. Let us take this example. Here, first of all, take this 10 to the left hand side, or you can take taking tan inverse both sides. You will get tan inverse P is equal to x minus P upon 1 plus P square. Taking this P upon 1 minus P 1 plus P square to the left hand side, we will get the value of x as tan inverse P plus P upon 1 plus P square. That means x is expressed in terms of P and y. In fact, y is not present here, so no problem. Even if the y is on the right hand side, our purpose is solved. We have expressed x in terms of P and y. Now what to do? Differentiate both sides with respect to y now. So here you will get dx by dy is equal to derivative of tan inverse P is 1 upon P square plus 1 plus derivative of this is P square plus 1 square in the denominator, then P square plus 1 into derivative of P is 1 minus P into derivative of 1 plus P square is 2P square. But the problem is we are differentiating with respect to y, and here we have differentiated with respect to P. So there should be dP by dy here. This dx by dy, we know that P is dy by dx. So what is your dx by dy is 1 upon P. 1 upon P is equal to, solving this inside bracket, you can take P square plus 1 whole square as the LCM. You will get P square plus 1 here plus, now solving this you will get P square plus 1 minus 2P. Here it is 2P square I have written, but it is not 2P square, it is 2P, sorry. So multiplying it will become 2P square and dP by dy outside the bracket. This P square and minus 2P square will be cancelled. What you will get? You will get 1 upon P is equal to, this is 1 plus 1 is 2 over P square plus 1 whole square dP by dy. Taking dy to the left hand side and this P to the right hand side, you will get dy is equal to 2P upon P square plus 1 whole square d. And now the remaining job is very easy. Just integrate both sides to get the value of y. And I think you can do it because it is the very elementary job, just elementary uses of integration. Now you will get the value of y. Value of x is already here. So this equation, value of x here, and whatever the value of y you will obtain from here, these two together will give you the solution of the given differential equation. So this is the solution when the differential equation fxyp is equal to 0 is solvable for x. Now we take a very interesting case, that is Clairaut's form. What is the Clairaut's form? Whenever an equation is expressible as y is equal to px plus some function of p, then we say that this equation is in Clairaut's form. Now, if the equation is in Clairaut's form, how to get the solution? It's very easy. Just differentiate both sides with respect to x, as we are doing in the case solvable for y. This is always also solvable for y. So derivative will be dy by dx in the left hand side. On the right hand side, we are taking here this p as a constant and derivative with respect to this is now p into derivative 1 plus x into derivative of p is dp by dx. What is this dy by dx? Is p. So p is equal to p plus x dp by dx. P will be cancelled. You will get dp by dx is equal to 0. Integrating, you will get p to be a constant. And just substitute this value of p to be a constant in the given differential equation. Y is equal to cx plus some function of c will be the solution of this differential equation. So now it is clear that if a differential equation is in Clairaut's form, y is equal to px plus fp, the solution we need not to solve. We are just to substitute p is equal to c and we will get the solution y is equal to cx plus f of c. Just as an example, suppose you are having y is equal to px plus sine inverse log of p upon 1 plus p. Suppose this is your differential equation. Since this differential equation is in the Clairaut's form, y is equal to px plus some function of p, the solution will be straightforward. Just replace p by the constant c and the solution will be y is equal to cx plus sine inverse log of c upon 1 plus c. This is the direct solution. Now, some differential equations are not directly into the Clairaut's form, but they can be reduced to the Clairaut's form. So, one such example, we can take y square is equal to 2px plus y square p square. Consider this differential equation. This is not in Clairaut's form but can be reduced. How? Multiply both sides of this equation by, it is y here, not y square. The equation is this. Now multiply both sides of this equation by y. It may be that the equation may be not correct. I may have to alter the equation accordingly. Multiplying both sides by y, what you are going to get, y square is equal to 2py into x plus y cube p square. Here I think I am getting some problem. So take here y, not y square. So what we will get here, we will get y square here. Because otherwise this equation will not be reducible to the Clairaut's form. If this will be the equation, this will be converted to the Clairaut's form. How? Take this y square to be some other variable, you can say z, and then differentiating, you will get 2y dy by dx. dy by dx means p is equal to dz by dx. dz by dx you can say p dash. Here p dash is dz by dx. 2py is equal to p dash. Now what this equation is going to take the form? This is y square, so y square is z. Okay. This 2py is p dash, so it is p dash x plus, here you can write 2py whole square divided by 4. You can write like this. So what it is now, z is equal to p dash x plus this 2py is p dash, so it is p dash square by 4. And now this equation is in the Clairaut's form. This is z is equal to p dash x plus some function of p. Doesn't it look like that y is equal to px plus function of p? You can compare this equation to this one and now it is in the Clairaut's form. So what the solution will be? The solution will be very easy. Just replace p dash by the constant c. The solution will become z is equal to cx plus c square by 4. And now substitute the value of z. Here z was y square, so y square is equal to cx plus c square by 4 is the solution of this differential equation, which was not in Clairaut's form, but we reduced it to the Clairaut's form, and then just replacing the p dash by c, we obtained the solution. So we are stopping this lecture here. In the next lecture, we will discuss more methods of solution of differential equations. And I am looking that you are enjoying these videos, you are solving differential equations using these methods, you are liking, you are sharing, you are subscribing the channel. I am really thankful to you, and I hope in this video also you will like it, you will share it, you will subscribe it to get more and more knowledge of differential equations, topology and knowledgeable entertainment. Thank you very much.